Okay, now we want to discuss something called final value theorem. Up to this point, when we have all we have studied in this course has been different ways to model a system. We started with assuming that you know uh, what a differential equation is and how we can use that to describe dynamics of a system. Then we studied transfer functions. In order to study transfer functions, we needed to learn Laplace transform. Then we studied block diagrams, and then we studied state space representation. All four of these are different ways that we can describe a system. What does it mean to describe a system? It means to model the system. It means to write down uh, how, or basically point at a relationship between input and output of a system. Starting now, we want to learn about behavior of systems. So, given one of these different ways to describe a system, can you tell me what the behavior of the system is? Specifically in this course, we want to focus on transfer functions. So if I give you the transfer function of a system, if I say I have this system with the given transfer function, so I have some poles, I have some zeros, can you tell me if there is any input that for that specific input, there doesn't exist any output? If I give that input to the system, no output is going to be generated. Do we have such an input? At the end of the course, we learn how to modify the behavior of a system. So having a specific kind of behavior, what can I do to change that output or behavior of the system? So what we study today is final value theorem. You have studied final value theorem in other courses. It's a math equation. It has nothing to directly do with controls, but we use it here in systems and controls. So what final value theorem says is that consider a function of time, or a mathematical function which has Laplace transform y of s. So you describe the function in time as y of t, and you describe the Laplace transform of it with capital Y of s. Final value theorem states that if you take the limit of that function at infinity, the value that you get, so the final value of that function, is equal to limit of this Laplace domain form of that function evaluated at the origin, but also you have to multiply it with an s. So if I have a function of time and I want to see at the end of the day what happens to it, what I can do is to take the Laplace transform of it and multiply that by an s, and then evaluate what I have at the origin. But there are restrictions. I can't apply that to all functions. Functions that I can apply final value theorem to have these limitations. Okay, let's see what the limitations are. It says where a simple pole of y of s at the origin is permitted. So y of s, the transfer function, can have a simple pole at the origin. So it can have an s in the denominator. But poles on the imaginary axis and in the right half plane and repeated poles at the origin are excluded. So if y of s has poles that are on the right hand side, so they have positive value, or they are on the imaginary axis and the j omega axis, or if it has two poles at the origin, you can't use final value theorem. Let's see these examples. Consider the following output functions. So I have some functions. I have represented them or described them in Laplace domain, and I'm asking you for which one can you use final value theorem. Okay, so you want to use this equation 7, but wait a second, I want to see if I can apply it. Okay, so can I apply final value theorem to this? What are the poles of the system? This means that I have a pole at 0, so s equals to 0 is a pole. This means that s equals to -4 is a pole, which is on the left-hand side. So the restriction I have is that it is okay to have one pole at the origin. It is not okay if I have two poles at the origin. So repeated poles are not allowed. Poles on the right-hand side, so positive value, and imaginary axis are not allowed. This does not have any poles on the right-hand side, on the j omega axis, and there is one pole at the origin. So this is okay. I am able to apply final value theorem to this. How about here? Well, let me look at the poles. I have a pole at the origin, and I have s squared plus 2, which means I have two poles at plus minus j square root of 2. Let me show you. So these are the poles. These poles are on the j omega axis. These are purely imaginary numbers, which means that they are not allowed. So I cannot apply final value theorem to this system. For the third one, there is one pole, and that is at positive 4. Therefore, we cannot use final value theorem for this system. For the following functions, can you use final value theorem? If yes, do it. Find the final value of this function. Again, I evaluate this function. I have one pole at the origin and another one at -8. So I am able to apply final value theorem. Here I have s equals to 0 and -4 divided by 5. So yes, again, I can apply final value theorem. So to find limit of y of t goes to infinity, I can just take the limit of s times y of s when s goes to 0. So s is simplify, evaluate this at 0. I have -7 divided by 8. Similarly, here I have simplification, and then I have 0.5 as the final value.